This is Bob Capetta from the University of Illinois at Chicago, and this lesson is on horizontal asymptotes for rational functions. So let's remind ourselves what a rational function is. R of x is p of x over q of x. P of x and q of x are both polynomials. Now, remember what a polynomial is. Some number times x to some power plus some number times x to some power plus some number times x to some power, etc. The powers all have to be integers, and the numbers are real numbers. So we have things like 3x squared plus 5x plus 1 is a polynomial, 2x plus 7 is a polynomial, 3 is a polynomial, 9x cubed plus 4x squared plus 13 is a polynomial. So that's the form they take. The highest power is called the degree of the polynomial. That's going to become important for us as we continue our discussion on these horizontal asymptotes. So here's an example for us to look at. F of x is x plus 3 over 2x squared plus 7x plus 1. These are both polynomials, and we want to determine whether or not there is a horizontal asymptote. If we look at the graph, what do we see? Well, we see these various pieces, but they're all getting closer and closer to the x-axis as the x values get very, very large. So it appears as if the x-axis is a horizontal asymptote, or if you like, the line y equals 0 is a horizontal asymptote. So let's take a look at another example. So we have g of x is 3x squared plus 5x plus 2 over x squared minus 3x plus 4. Both of those are polynomials, so it satisfies the conditions of being a rational function. Now we're interested in identifying the horizontal asymptote, so let's look at the graph and see if we can determine what that's going to be. So there's our graph. You'll notice we have a horizontal line here at y equals 3. That on the right-hand side, as x goes to positive infinity, the function seems to be getting closer and closer to 3. As the x goes to negative infinity, the function seems to be getting closer and closer to 3. So y equals 3 here is going to be a horizontal asymptote. Look at another one. What if we have x plus 3 over 2x squared plus 7x plus 1? We want to identify if there is a horizontal asymptote. So we'll look at the graph. And what do we have here? Three pieces, all getting closer to the x-axis, all getting closer to 0. So again, the y equals 0 is a horizontal asymptote. This one, 2x squared minus 7x plus 9 over x minus 2, what do we have there? A situation like that. There does not appear to be a horizontal asymptote there, but you might argue there is a slant asymptote, an oblique asymptote, and that's something we'll look at in another lesson. So no horizontal asymptote here. As x gets large, it doesn't settle down. The function gets large. As x gets large negative, again, it doesn't settle down. The function gets large negative. So no horizontal asymptote here. But we see the oblique asymptote. We can kind of squeeze a line in and then follow that path. So here's our first case. If the degree of the top is less than the degree of the bottom, I'll call that a bottom-heavy fraction. So here's an example. The degree of the top. The highest power of the top is 1x to the first power. The highest power of the bottom is 2x to the second power. This is a bottom-heavy fraction. If you have a bottom-heavy fraction, when x gets really, really large, like a million squared is so much bigger than anything else that the 7x plus 1 becomes irrelevant. So a million squared is a trillion, times 2 is 2 trillion. A million and 3 is basically a million, but a million divided by a trillion, a million is nothing compared to 2 trillion. So as these numbers get really, really large, this x squared dominates. It's so much bigger than anything else that the function is going to go to 0. So again, in this case, the degree of the top is 1 and the degree of the bottom is 2, as we've seen here. And there is that situation with the horizontal asymptote at y equals 0. So when you have a bottom-heavy fraction, when the degree of the bottom is greater than the degree of the top, then y equals 0, also known as the x-axis, will be a horizontal asymptote, always. For a rational function that is bottom-heavy, where the degree of the bottom is greater, again, this too is the issue. x squared versus x to the first. This 2 is bigger than that 1. A bottom-heavy fraction, you'll have a horizontal asymptote at y equals 0. So here's another case for us. 2x squared plus 4x minus 1 over 7x to the fourth plus 3x cubed plus 7x squared plus 5x plus 1. Is this bottom-heavy? Highest power of the top, 2. Highest power of the bottom, 4. Bottom-heavy fraction. So if that's the case, there should be an asymptote at y equals 0. Do we see it? You can sort of see it, that we have all this crazy stuff going on in the middle, but as the function settles down, as we go into large negatives or large positives, the function starts to kiss the x-axis. So indeed, the x-axis or the equation y equals 0 is a horizontal asymptote. What's our story here? When does that happen? That happens when we have a bottom-heavy fraction when the degree of the bottom is greater than the degree of the top. So here's our official rule here. If the degree of the numerator is less than the degree of the denominator, the x-axis is a horizontal asymptote, and the equation of the x-axis is y equals 0. Bottom-heavy fractions behave that way. Our next case is when they're the same. So for case 2, the degree of the numerator, the top, is the same as the degree of the denominator. So I have x squared on top, I have x squared on the bottom. Both of those are the same order. So if we have the same order, we will also have a horizontal asymptote. What will that look like? So here's our function, and there's the graph. So you'll notice this line here at y equals 3 is the horizontal asymptote, that as x gets large, as x goes to positive infinity, the function gets closer and closer to 3. As it goes to negative infinity, the function gets closer and closer to 3. So y equals 3 is going to be the asymptote for this problem. And I want you to notice that the ratio of the highest powers, if we ignore everything else, forget about 5x and 2, forget about negative 3x and 4. The highest powers are what dominate. 3x squared divided by 1x squared would just give us 3. And that's the process. That's how this one works. So looking at this example, we have f of x is negative 6x cubed plus 4x squared minus 2x plus 1 over negative 3 plus 4x plus 5x squared plus x cubed. Highest power on the top, highest power on the bottom. Highest power on the top, x cubed. Highest power on the bottom, x cubed. They are the same. Degrees on the top and the bottom are the same, so we will have a horizontal asymptote. We ignore everything else. Ignore all of this, ignore all of this. Just looking at the highest powers, negative 6x cubed over 1x cubed gives you an indication of where that asymptote should be. So there's our picture. This is the point 0, negative 6, and here is the asymptotic line, which of course is y equals negative 6. Where did negative 6 come from? Highest power here, negative 6x cubed. Highest power there, 1x cubed. The ratio of those two pieces is going to give us negative 6. Hence f of x equals negative 6, or y equals negative 6 is the end term behavior for this function. Y equals negative 6 is the horizontal asymptote, and again the ratio of the highest powers, negative 6x cubed over 1x cubed, is negative 6. So here's a formal look at that second case. If the degree of the numerator, the top, is the same as the degree of the denominator, the bottom, then there is a horizontal asymptote. It is of the form y equals a over b. A is the coefficient of the highest power of the numerator. B is the coefficient of the highest power of the denominator. So in this example, a is negative 6, b is 1. Coefficient of the highest power, negative 6 here. Coefficient of the highest power here, 1x cubed. So indeed, y equals negative 6 over 1, or y equals negative 6 was the horizontal asymptote for that example. Now here's our third case. If the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. I call that a top-heavy fraction. If the degree of the top is bigger than the degree of the bottom, no horizontal asymptote. The degree of the top here is x to the third. 3 is the degree. 1 is the degree there. We do not expect a horizontal asymptote. And there's a funny looking graph. Long-term behavior as x gets large, the function gets large. As x gets large negative, the function gets large positive, or so it appears. So there's no stabilizing. The long-term behavior just continues to grow and grow and grow and grow. It doesn't stabilize on a single number like the other horizontal asymptotes we saw. Here's another example. 2x squared minus 9x plus 1 over 7x plus 3. We just, again, focus on the highest powers. It's top-heavy. So it's not going to stabilize. If you're top-heavy, you're not going to have a horizontal tangent. So if we look, again, we can see no horizontal tangent. But something is interesting. As x gets large positive, the function grows, so the function's getting large positive. As x gets large negative, the function goes this way, gets large negative. But you'll notice we could probably squeeze an asymptote in between this. A slant or an oblique asymptote, indeed, will be what's going to happen with this problem. So no horizontal asymptote there. So here is our conclusions. If the degree of the numerator is less than the degree of the denominator, the x-axis, or the line y equals 0, is a horizontal asymptote. If the degree of the numerator is the same as the degree of the denominator, then there is a horizontal asymptote made up by the two coefficients. And finally, if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. And that will end this lesson.